Well, the usual way that people discuss it is to talk about perfect squares first. So if you have studied the Pythagorean theorem, there's a formula that the square of the hypotenuse is the sum of the two squares of the sides of a right triangle. So you might ask, if the sides of a right triangle are whole numbers, might it happen that the hypotenuse is also a whole number? They're called Pythagorean triples, and the Greeks figured out all of the Pythagorean triples. Okay, so what happened next is, I think it must have been very natural to look at the equation a cubed plus b cubed equals c cubed, and a to the fourth plus b to the fourth equals c to the fourth, and so on. So this is now in the realm of algebra, and you can plug in values for a and b, and you'll see that these equations, infinite number of equations, seem not to have solutions. Well, so the story is that Fermat was reading the text of Diophantus, who is the Greek mathematician best known for this type of problem, and in the margin of his copy of Diophantus, he wrote some marginal notes saying that I can prove that for higher exponents, bigger than 2, there are no positive integer solutions. And then famously he said, but my solution is too long to write in this margin. And in his copy of Diophantus, which was inherited by Fermat's son Samuel de Fermat, there are many, many marginal notes. And Samuel published a revised version, an annotated version of Diophantus's book, in which all of his father's writings are reproduced. And the reason that Fermat's last theorem was called Fermat's last theorem is that all of the previously examined marginal notes proved to be correct, or at least they were proved to be correct or incorrect, mostly correct, by mathematicians after the 17th century. And there was this only one assertion that remained. It was the last one on his hit list. And, you know, again, I'm not an expert in the history of mathematics, but I think most people are convinced that when Fermat was a mature mathematician, he realized he did have no proof of this thing that he wrote in the marginal note. And in fact, later in his life, he devoted a lot of attention to special cases of that type of equation. So it's not just the cubes, but it's the cubes and the fourth powers and the fifth powers and so on. And Fermat himself, later in his life, took care of the fourth powers. Well, the cube certainly must have bothered him, because after all, he knew about squares and he knew about fourth powers, and cubes were right in the middle.
The theorem is that there is no solution. There's no whole number solution.
That's right.
Yeah. Would it have been, or would it have been more exciting or more attractive to a mathematician to prove him wrong and to find these three numbers that you could plug in that would do it? Would that have been more triumphant?
Well, it would have been very exciting. It would have made lots of news, and then the proof, so to speak, would have been simply a single counterexample that would have fit, you know, very neatly in a newspaper column, you know, and there would have been some story, you know, mathematician in Australia finds the first counterexample to Fermat's last theorem. Certainly it was big news either way. The main thing about Fermat's last theorem is that over the centuries it gave rise to a tremendous amount of new and fruitful mathematics. That people really developed new techniques to try to solve that equation that proved to be, you know, infinitely versatile.
So a bit like going to the moon, let them develop lots of other technologies along the way. This was the going to the moon of mathematics.
That's a fine analogy. I mean, when you formulate a problem in mathematics, no one knows whether this problem will really be helpful for mathematics as a general enterprise. And, you know, for whatever reason, Fermat's equation has led to a tremendous amount of new mathematics. So when I was a graduate student, we're talking, you know, roughly 40 years ago or 45 years ago, Fermat's last theorem was kind of some curiosity. Everybody knew about the problem, but no one really had any approach to it. And there was no kind of fundamental reason why the problem was going to have a positive solution. And when I was a student, there was a tremendous interest in what are called elliptic curves. And it was realized around 1968, 1969, 1970 by Andre Weil and Goro Shimura in Princeton, who built on the work of Yutaka Taniyama, who was his buddy in Tokyo in the 1950s. Taniyama had passed away, and there was this gradual understanding that elliptic curves really were related to modular forms. And again, that was some completely apparently inaccessible, outstanding conjecture, and it was thought to be an incredibly hard conjecture. And then in the early 1980s, a mathematician came around, and I say that literally because he was sitting here in this office. His name is Gerhard Frey. At the time, he was at the University of the Saarlands in Saarbrücken. And he came...
Is that a famous one? I don't know that one.
Well, I didn't know it either. And he came around and he had this scheme for relating Fermat's last theorem and the modularity conjecture. Somehow he realized for the first time that if he had a solution to Fermat's equation, this would give him an elliptic curve which apparently could never be modular. I was a little skeptical because I knew that some of the things that he said that he needed in his argument were very hard. Well, for me, a really important thing was in 1985, Jean-Pierre Serre, who's one of my mathematical heroes in Paris, sat down and kind of tried to distill everything that had been said about Frey's idea, and he came out with a very clear letter. And this letter basically said, if you can prove this tiny little result, which he called epsilon, because in calculus, epsilon is a small number. He said, if you can prove this tiny little epsilon, then you can really show that the modularity conjecture, which he called Weil at the time, implies Fermat's last theorem. So epsilon became, for me, a holy grail because not only was it something fairly well encapsulated and very clear, and this was the kind of thing that I'd thought about before without success, but nonetheless, while thinking about yet another problem, it occurred to me that I really had some new information that I could possibly bring to bear on this epsilon. What I first did was say to myself, what's the simplest possible case where I can think about this? What's the simplest possible prediction? I tried to settle that. I said, well, if you have to start somewhere, I know about this simplest case, so I had this thing in my mind and I thought about it off and on during the academic year, 1985-86. And during this year, I was teaching calculus. I was busy with things. Colleagues come in, they want you to be on committees. And finally, my final grades were submitted in May 1986. And I started thinking about this problem again. First, I was on the East Coast for a while, going to Europe, and then I found myself in Paris, and finally I found myself at an empty desk in the Max Planck Institute in Bonn, where I could just sit and think. And I thought about this yet again.
Is that what you do? Do you just sit at a desk with your head in your hands and think? I mean, what if I was a fly on the wall when you were trying to crack this problem? What would I have seen? What does it look like?
Well, it's probably, I probably had a pad of paper in front of me and a pencil or a pen. We didn't really have computers quite yet, although they were starting to come. And when you visit some institute, you don't have all your stuff with you. You don't have lots of books, you don't have all your paraphernalia. So I was really just kind of sitting there like that. And I started writing, and if you look in my office, you'll find lots of old pads where I sit and write, and the page might start, what do we know? What are we trying to do? Let's summarize the situation so far. Let's try this. And to my astonishment, I was finally able to crack that problem, the simplest case of epsilon.
So inspiration comes at preordained times. Like you sit down and say, okay, for the next 2 hours before I meet my friend Bob for a hot dog, I'm going to have an inspiration and try and solve the problem. And that's when it happens. It doesn't happen at odd times when you're lying in bed. Or
it can. I mean, if you think about something very intensively, then you just carry it around with you. And, lots of my colleagues say that while they're swimming, they had some insight. Or, lots of people say in the middle of the night, they jumped up and they said, my God, why don't I try the minus sign instead of the plus sign? And this can indeed happen,
Not for you, though. You're at the desk kind of guy.
I think in this particular situation, I was at the desk. I knew for the first time that I could do something that I hadn't done before, that no one had done before. This was a special case of this so-called epsilon. And I kind of wrote it and rewrote it just to make sure I was really right. And finally, using the very first Macintosh that I had access to, I typed out a letter to Barry Mazur at Harvard, and I sent him this letter explaining what I'd done. And then I spent weeks and weeks trying to do the general case. I couldn't see what to do. And then, fortunately, there was an International Congress of Mathematicians. They occur once every 4 years on the campus of UC Berkeley. So I was right here. I came back in August for this International Congress, and Barry Mazur was there. And I spoke to him, and I said, Barry, I sent you this letter explaining how I did a special case, and I really wonder, what I have to do now to do the general case. And he looked at me completely quizzically, and he said, well, but you've already done the general case. And basically, he, when he read my letter, it just seemed obvious to him that there was this extra little thing you carry along as a supplemental object, and this extra thing would just do the bookkeeping. And so we sat down at this Cafe Strata, which is at the corner of the Berkeley campus, and we had a cappuccino, and he kind of said, well, you just carry this around with you. And I was astonished. It was like this amazing moment where all of a sudden I realized that, in principle at least, there was no obstacle to proving this epsilon conjecture. I mean, it's like, my God, it's some special thing. An angel comes down and a light shines from the heavens or something. So this was really quite a thing. And since all of my colleagues were walking around the campus in this big international congress, I kind of told, a number of them that I had done this thing. Of course, in the beginning I was cautious. I said, well, I think I've done this thing. But people kept running up to me and they said, well, is it really true you've done epsilon? I lived in a world, and think I still do, where my colleagues are very generous with attributions and praise, and there isn't too much of this kind of race to be the first to publish. And people basically, I had little fear that someone would try to scoop me. On the other hand, what was a little worrisome was that I hadn't written down all the details. So I kind of had written down very closely the special case, but I hadn't kind of worried about writing the thing more generally. So what happened was that during the year following that, 1986-87, there was a special program on algebraic geometry and arithmetic geometry at the Mathematical Sciences Research Institute in Berkeley, the MSRI. So I was up there with my colleagues, and I gave lectures. Every week I gave another lecture. I was kind of giving like a mini course on my proof. And when I wasn't lecturing, I was furiously typing into the computer to try to expand and revise my manuscript. And kind of more and more details got put in. And there were certainly people in the audience who were appropriately skeptical. They asked me hard questions, and I didn't always know the answer to the hard questions. Well, how do we really know that this thing is in such and such way? And I would say, well, this was proved in the 1960s by Grothendieck, but it isn't quite written down in the place you expect. And then I'd have to go find an argument. Well, epsilon was not small. It was clearly a misnomer. And let me just get up and pull off a reprint. Here's my article. It was published in 1990, which really makes a lot of time between 1986 and 1990.
How many pages?
So it went through.
It's like a book.
Well, it's more than a pamphlet. If you open up this paper, on the very first or second page, there's Fermat's equation and an elliptic curve, but then they disappear. If you look at the actual article, it's more about the technicalities of the subject. It was a big deal in mathematics. It got write-ups in the press, including Science Magazine, if I'm not mistaken. Whenever there's a serious announcement of a major theorem, that gets a lot of attention, and people stop what they're doing to try to see what the basis of the proof is.
Who calls it Ribet's theorem? Obviously you don't get to make that name up. That just sort of evolves, does it, whenever a mathematician does this?
Well, yeah, that's right. So you certainly, there's a general aversion to naming things after yourself. So very often people will give lectures and they'll say such and such theorem, and then in parentheses they'll write the name of the person who proves it, and if it's a theorem that they prove themselves, typically they write the first initial of their last name or something like that. Or else they don't add any attribution, and the listeners understand, well, this is the theorem that the person is providing in this lecture.
You've done this thing which is important. You've built a bridge between two things neither of which are on solid ground yet, though.
Well, that's right. So what I showed was that this modularity conjecture, which was thought to be, was felt to be true, but wasn't expected to be provable, I showed that that thing actually implies Fermat's last theorem. I think the main takeaway from my theorem was that since the Weil conjecture, or Shimura-Taniyama, was likely to be true, that now you should think that Fermat's last theorem was likely to be true. For example, it probably wouldn't have been a really good idea to spend a lot of computing power looking for a counterexample to Fermat's last theorem.
Where was Andrew Wiles? He was in the room?
Well, that was the whole thing. So Andrew Wiles, you know, of course he came around a few times, I guess, but basically he was holed up in his attic. And I didn't know that, and I think most people didn't know that. So he was, I mean, it's his statement that he was certainly intrigued by Fermat's last theorem as a child, and that as soon as he heard about this bridge, he decided to try to prove the modularity theorem because of its relation to Fermat's last theorem.
So is it sort of the situation that Andrew Wiles wanted to prove Fermat's last theorem by any means possible, and you'd given him a new means?
That's what he says. I mean, this is surprising to me because the modularity theorem by itself is a tremendous prize. And, you know, it seems kind of strange that you needed the motivation of Fermat to go and try to prove it if you thought that there was some way.
That's not strange to me.
Well, anyway, that's what he says.
But yeah.
We were all together, meaning kind of lots of people in the subject, in a conference in Cambridge, England in June 1993. And usually you go to a conference and you see the list of speakers, and you know each speaker has an hour. And the thing had been set up so that Andrew Wiles had 3 hours. So he asked the organizers, he said, I have something I want to discuss and it will take me 3 hours and I'd like those slots. And they said, okay. And then in the first lecture, you could see he was proving, he was starting to prove the modularity of some class of elliptic curves. But the class of elliptic curves, at least in the first lecture, had no intersection with the class that you needed for Fermat's last theorem. But then the second lecture got a lot closer, and it became more and more apparent to people at the conference that in the third lecture, he was going to be able to do enough to get Fermat's last theorem. The crowd was growing, so a lot of the mathematicians, you know, brought their colleagues who happened to be in Cambridge, and you know, some of their family members, and I think there was little doubt that he would announce a proof of Fermat's last theorem. So I came and I sat in the front row center and brought my camera and snapped a picture of it. That was another moment when, you know, this kind of time stopped, and when I first realized what was going to happen. And then, you know, when it actually did happen, there was this frenzy of activity. I mean, the director of the Isaac Newton Institute, where these lectures were held, had ordered a case of Napa Valley Brut, champagne, for the end of the lecture. And as after the lecture, we came out into the, you know, common area, and all these champagne flutes were produced, and these bottles started popping, and you know, it was kind of really an amazing thing.
Between the time when you built your bridge and you published your paper and this lecture, did Andrew Wiles ever call you or write you and ask for your help? Or
Not a word. Not a word.
You had no idea?
I had no idea what he was doing.
You knew who he was, though. He wasn't like a nobody. He was
Oh, absolutely. He was a friend and a colleague. I first met him when he was a graduate student in Cambridge. And in fact, when I first came to Berkeley, the first year that I was here, he was one of the first people that I invited. He came and spent a week and gave a lecture or two.
Do you like that? Do you like that he kept it a secret? Does that make it like a nice surprise party? Or to this day, do you feel baffled by it? I mean, you seem a lot more collegiate. You're telling me when you solved your thing, you were running around telling everyone, and he's quite secretive.
Well, it's very unusual behavior. And, you know, you can say in retrospect that it was really justified because he was afraid that people would kind of jump all over it because of the importance of the modularity conjecture and Fermat's last theorem. But he did not tell me what he was doing. He did confide in two of his colleagues at Princeton as he was giving his graduate course where he was working out the ideas that were instrumental in his paper. I think it was only a few days later that I got a copy of this manuscript. And the manuscript was very thick, you know, it was like 300 pages, single space, you know, typeset by TeX, mathematics typesetting program. And we were supposed to be the kind of referees looking at different parts of the paper, and I was assigned to a part that turned out to be problem-free. Nick Katz looked at a part that turned out to have problems, a problem.
Was that shattering for you, or do you like that? Does it make you think, this is good, you know, I like the rigor, this is how mathematics works, or was it really deflating after the high of the champagne?
You mean finding the problem? Well, one of the aspects of the whole thing is that I had gone out pretty far on a limb telling everybody that Andrew Wiles had proved this thing. And the way that started was that when the New York Times first heard about his announcement, they asked to speak to him, and Andrew turned to me and said, Ken, you know, you speak to Gina Colada. So I went upstairs and spoke to her for a very long time, explaining the whole thing. And then somehow the media kept calling me because it was understood that somehow I was his designated spokesperson. So I spent that entire summer lecturing about his theorem and fielding phone calls from the press.
How long after the Wiles announcement did Katz find the hole?
Oh, I think it was like 2 weeks. What happens, see, in mathematics is if you have a proof that seems to really be, seems to have a lot of internal logic to it, and there's something that's wrong with the proof, your immediate reaction is to say, well, you know, this is just some technical problem that I need to fix. And I think that Andrew Wiles, when he found out about the gap, expected that he would be able to repair it in short order. So it really took a while before there was realization on his part that this was a serious problem that couldn't be fixed immediately just by the tools in front of him.
If you were the person who was taking all the calls from the press, for whatever reason, did that mean you were contacting Andrew Wiles a lot and saying, can you give me an update? Because I'm getting all these calls, mate, and I don't know what to tell them. Like, were you calling him for updates so you knew what to say, or had he gone to ground?
Not especially. He kind of went dark. He was working on mathematics, and I wasn't getting a lot of information out of him at that time. You know, it was all poised in the balance, right? I mean, wasn't clear whether or not this would get repaired or not. And then, you know, wonderfully, it turned out that there was this repair to the proof, really some completely new insight, actually, by Andrew Wiles and Richard Taylor, who worked together over the summer, and this would be the summer of 1994. And they had a preprint out in the fall of 1994, where they explained their new method, which is now called the Taylor-Wiles method. And that really circumvented a lot of the more complicated arguments in the original preprint. And the two articles were published together the following summer, which is the summer of 1995, in the Annals of Mathematics. It was a relief, but it was not a kind of joyous relief. You know, and Richard Taylor came to me one day, again at MSRI, where I happened to be, in the fall of 1994, and he said, we have some good news for you. And then the next day he handed me a copy of this paper. So that was kind of very good. And you know, I don't remember there being a huge celebration on the moment of the release of that reprint, but it just kind of gradually built. People understood that the proof was complete. And then there was a very large instructional conference at Boston University in the summer of 1995. Different people got up and explained the different elements of the proof. Well, it was a fabulous piece of mathematics. As impressed by what I did, as impressed as I am by my own work, I'm even much more impressed by what they did. They had some really new insight, and this insight has percolated through our whole subject for the last 20 years. One way to say what they did is they showed that somehow modularity is contagious, in the sense that if you have something that has a little piece of it being modular, you can parlay that into modularity of a full object. First of all, Wiles was obviously intensely driven to do this. He was really motivated, and he said, you know, I'm going to do this one way or another. And he brought in all sorts of different techniques that hadn't been related to the problem before. What's amazing, for example, there's a whole subject in algebraic geometry called deformation theory that was going on when I was a graduate student that I didn't learn. I thought that was really far removed from anything involving elliptic curves. And in the years before Wiles' announcement, Barry Mazur had developed this new technique of deformation theory in Galois representations, and it turned out to be exactly what Wiles needed, the language and the techniques that he needed for his discussion. And so, you know, something that seemed to be far away technically turned out to be crucial. Well, I think, you know, just informally everyone referred to it as the proof of Fermat's last theorem. But in fact, when you looked at the article, just like my article, it was something internal to the theory of modular forms and Galois representations. And Wiles' article and my article share the trait that Fermat's equation occurs exactly once in the article in the beginning, and then you get down to the real stuff. I'm very happy with the recognition that I've gotten, and I'm very proud of what I did. And when students come into my classes, they know about my role in Fermat's last theorem. A lot of them have seen the video that was broadcast on Nova and BBC. And I think, you know, if you do something very, 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 very famous, then you have an encore problem where people say, you know, what great thing are you going to do next? And I try to be more or less a normal guy and not, you know, walk around with angels on my shoulder.
Desperate to rediscover what Fermat's proof might have been.
Is it widely held that he had done it, or had he disclaimed? Like, was he telling the truth?
I think by the time we get to the 20th century, it's quite clear that this is an incredibly complex problem.